and welcome to part 3 of our lecture video series for Monday, May 8th. So let's practice applying the Clausius-Clapeyron equation. Do want to make a note here. I have a couple of sign errors in how you saw this in the last video. So I fixed this here. So the formula for the Clausius-Clapeyron equation is always 1 over 2 is equal to the negative heat of vaporization of 1 minus 2. So we always have to have 1 over 2, 1 minus 2. Keeps this negative. So make sure you fix that in your notes. And now let's practice a problem. So, all right. The boiling point of water is 100 degrees Celsius. If the enthalpy of vaporization of water is 40.7 kilojoules per mole, what is the vapor pressure of water at room temperature, or 25 degrees Celsius? So let's kind of start pulling some information out of this problem. The boiling point of water is 100 degrees. That was given right off the bat. So let's kind of remind ourselves about what we know about water and what we know about the definition of the boiling point. So remember, your definition of your boiling point is at your boiling point. By definition, any liquid at its boiling point has a vapor pressure of 1.00 atmospheres, because the boiling point is the temperature that it takes in order to achieve all of us being in the gaseous phase, meaning the pressure equivalent to ambient atmospheric conditions. So let's go ahead and call this condition 1. And we also know what this temperature is, right? So this is going to be P vape 1. This temperature is 100 degrees C. And if we look back up at our Clausius-Clapeyron equation, we see that it has this dependence on the gas constant re-expressed in joules per mole Kelvin. So I cannot leave this temperature in centigrade. I must put it in Kelvin. So plus 273.15 Kelvin gives 373.15 Kelvin. So let's call this T1. Okay, what else is given? If the enthalpy of vaporization of water is 40.7 kilojoules per mole, okay, I know that's important because if I look back at my Clausius-Clapeyron equation, it depends on the heat of vaporization or the enthalpy of vaporization. So this I can write as the enthalpy of vaporization of water is 40.7 kilojoules per mole. And again, let's take a peek back at our Clausius-Clapeyron equation. Again, it has this dependence on R, which is not expressed in kilojoules, but rather joules. So I can't leave this in kilojoules per mole. It needs to be in joules per mole. So I'm going to multiply this by 1,000. So I'm going to get 4.07 times 10 to the 4 joules per mole. Okay, then I was asked, what is the vapor pressure of water at room temp? So what is the vapor pressure? This is what we want. This is what we're trying to find. So we're trying to find the vapor pressure of a substance at some new temperature, specifically at room temperature. So T2 is 25 degrees C, and since we need to be in Kelvin, plus 273.15, this gives me 298.15 Kelvin. And now it's a question of plugging all of this into Clausius-Clapeyron. So I'm just going to rewrite Clausius-Clapeyron here. So the natural log of P vape 1 over P vape 2 is equal to negative heat of vaporization over R times 1 over T1 minus 1 over T2. So it's kind of always in order. This is how you can remember it. 1 over 2, 1 minus 2. All right. So P vape 1, this is our initial vapor pressure. We know this from our boiling point because by definition, at the boiling point, your vapor pressure is 1 atmosphere. So we do know the vapor pressure. And we also know the initial temperature, right? We know T1. Okay. What else do we know? We know the heat of vaporization of water. We'll have to make that sign negative. R is a constant, right? R is 8.314 joules per mole Kelvin. And then let's see here. Let's now start figuring out what we are trying to solve for. So what is the vapor pressure? So we don't know P2 at our new temperature, T2. So we do know T2. T2 is 298.15 Kelvin. So let's start plugging this in. So the natural log of our vapor pressure at our first condition, that's our vapor pressure at our boiling point, over the vapor pressure at our second condition is equal to negative our heat of vaporization, which was put into the correct units, 4.07 times 10 to the 4 joules per mole, over our R constant, our gas constant, 8.314 joules per mole Kelvin. Notice joules per mole and joules per mole cancel. This leaves a per Kelvin in the denominator. All right, times 1 over T1. So T1 was our boiling point, 373.15, minus 1 over T2, which was room temperature, 298.15. These are both in Kelvin. Okay, we've got things that are like plugged in and ready to go. But my advice is to kind of tackle this little bit by little bit. Like don't get too crazy. So we are going to first, I think, deal with what's inside these parentheses here. So like let's get what these fractions are. So we've got 1 divided by 373.15 Kelvin. So I get 2.67988 times 10 to the negative 3. And again, this is inverse Kelvin, minus, don't forget to open your parentheses when you do this, 1 over 298.15 Kelvin. I get 3.354 times 10 to the negative 3 inverse Kelvin. Okay, so we've at least gotten what those fractions are. How about we tackle this constant? So 4.07 times 10 to the 4 over 8.314, and then make it negative. So this is negative 4.895357 times 10 to the 3. And again, let's pay close attention to our units here. So this was 1 over Kelvin, right? Because there's a 1 over here. So 1 over anything just becomes that thing. So that becomes Kelvin. Still tackling this right-hand side. Okay, let's see here. Let's figure out what that difference is. So negative 4.895357 times 10 to the 3 Kelvin. All right, so we've got 0.00267 minus 0.003354. Okay, this gives me negative 6.7412 times 10 to the negative 3. Don't mind me, I'm just swapping in and out of scientific notation. That is all you need to do as well. All right, let's see here. I'm noticing that I've got a negative times a negative, so it's become positive. And also Kelvin and per Kelvin will cancel. So I now need to multiply this by my 4.895. So let's see here, 4.895, 357. Okay. When I do this, I get 3.30058. Wow, all right. And that was just our right-hand side. So let's kind of rewrite this. So now we have the left-hand side that we're not forgetting. So this is 1.00 atmospheres over our vapor pressure at room temperature that we're trying to solve for. This is equal to 3.300058. And let's remind ourselves that exponential functions and natural log functions are inverses of one another, meaning if I were to take the natural log of both sides of an exponential, that would undo the exponential. And here, if I were to now take e and raise both sides as an exponent of base e, that would undo my natural log. So this is going to be e raised to the natural log of 1 atmosphere over our vapor pressure that we want is equal to e raised to the 3.30058. And this is in fact e, it's not like our EE, which we've been using as times 10 to the. This is a number, just like pi is a number. This is Euler's number. You should have a lowercase e button on your calculator. And the whole point of applying this inverse relationship between these two functions is so that the e and the natural log cancel one another out, leaving behind 1.00 atmospheres over p vape. Okay, and then we have to do e raised to that number on the right-hand side. This becomes 2.71, nope, 2.7183. And nice little trick here. Yes, you could, multiply p vape over by both sides, but remember, anytime you have the structure of whole number equal to a fraction, then you can say that the fraction over the whole number is equal to the denominator. You can just literally, boop, swap these. So I now have 1.00 atmospheres over 2.7183 gives me my vapor pressure at 25 degrees Celsius. Okay, this gives me, if my calculator isn't a liar, 367,879 atmospheres. In other words, the vapor pressure at room temperature should give me, oh, computer, hush. 0.368 atmospheres. So the vapor pressure of water at room temp is this. All right, that was a lot. We're going to practice this on active. I can hear the booze already. So this is it's not a hard equation, right? It's just got a lot of components, right? There's negative signs, there's inverses, there's, a constant that's now in new units. There we got to make sure that we're doing 1 over 2 and then 1 minus 2. We got to do natural logs and exponents and such. So make sure that you're feeling technically competent with how to apply the Clausius-Clapeyron equation, because this will be showing up on our final. All right. So now that we've practiced the Clausius-Clapeyron equation, let's just do a little intro to phase changes, because we've kind of already talked about them at the beginning of the year, but let's talk about them now in terms of energy. And then we will talk about the remaining phases, which are our liquids, and then a little bit of solids to close out the year.